In engineering, we often assume that a pristine paper document rolling off the specification assembly line means the job is done. The standard belief is that if a requirement is unambiguous, verifiable, and internally consistent, it is ready for production. Teams spend hundreds of hours training to meet strict ISO standards and applying structured syntax templates to ensure every sentence passes technical muster. Yet, these syntactically perfect, technically accurate instructions regularly hit downstream teams and trigger a backlog of requests for technical clarification. The problem lies in perspective. The author sees precision in their own highly technical phrasing, but the reader lacks the same context. When we prioritize sentence structure over the actual operational workflow of the person doing the reading, we create a functional breakdown in cross-functional collaboration. Consider the standard sequence in automotive manufacturing. An electronic and tool unit designer writes a specification, hands it to a supplier to build the hardware, who then passes the tools to a service engineer out in the field. The original designer naturally falls into an author-centric trap. They write using the implicit knowledge of their immediate team, relying on specific toolchain shorthand to define logic. The moment that document crosses organizational boundaries, the shared context evaporates. The clean specification fractures into conflicting interpretations. The result is a workflow characterized by repetitive clarification cycles and renegotiations that stall project progress. The solution to this specific failure mode is a framework called Reader-Centric Requirements Engineering, or RCRE. Its core metric is consumability. Consumability asks how easily the intended reader can translate text into their next action. Syntactical well-formedness is necessary, but consumability becomes the primary measure of success. To see how implicit meaning drains resources, we can look at a specific case study in heavy-duty truck diagnostics. An internal combustion specification reads, condition expression, CF_EVRDY equals 1. To the designer, this maps to an internal database with absolute brevity, but the supplier is forced into massive external database searches to determine the physical engine state. By encoding precision exclusively through specialized shorthand, the author has turned a simple instruction into a high-friction interpretation project for the supplier. RCRE addresses this through its first operational pillar, Interpretability. This measures how quickly a reader can find the answers to their specific operational questions. A specification must deliver explicit meaning at the point of use, avoiding the need to hunt down unwritten assumptions in an external glossary. The author translates the code into a plain operational state using local mapping. Integrating the technical identifier alongside the definition, the RCRE rewrite combines both. Vehicle is in drivable or ready state. Implement as CF_EVRY equals 1. This short interpretation path removes the need for external database searches, lowering the reader's cognitive load. Once the reader understands the text, we reach the final step in the process, actionability. Defining correct detection logic is distinct from providing usable execution guidance. Downstream roles need explicit next action hooks. A supplier needs implementable constraints to build the hardware, and a service engineer needs specific triage steps to respond to errors in the field. These executable decision points must be positioned adjacent to the triggering conditions in the specification document. Without these actionable hooks, a supplier might comprehend what a system must do, yet remain blocked on how to actually build and test it. Taking these concepts into routine industrial execution requires a rigid mechanism. The engineering team enforced this framework during their monthly review cycles using a tool called the Requirements Profile, or RP. The RP enforces reader-side sufficiency criteria. It acts as a checklist tailored to the workflow of the diagnostic teams consuming the documents. It demands core structural items, like explicit fault code conditions and exact clearing time parameters. It also mandates secondary requirements, including warning lamp behaviors and specific limp home instructions. These contextual targets are designed to satisfy cross-boundary consumers. The RP checklist translates theoretical consumability into a measurable operational baseline. This chart shows RP satisfaction rates across internal combustion and hydrogen electric lines, spanning 94 control units and over 8,000 diagnostic requirements. Initially, only about 30% of requirements met the criteria. After applying the RCRE framework in round 1, satisfaction increased to approximately 90% as core gaps were resolved. A second review addressed minor mismatches, pushing satisfaction above 92% for combustion units and 96% for the hydrogen line. Following these improvements, the specific categories of issues identified by the profile were no longer raised in the regular monthly review meetings. This micro-evidence is specific to heavy-duty truck diagnostics. Applying the RCRE framework to other engineering domains requires mapping the downstream workflow and tailoring the RP checklist to those specific users. Traditional requirements engineering often places the burden of interpretation on the reader. RCRE shifts that burden back to the text itself. Syntactical well-formedness and correct template usage remain critical, but they act as prerequisites for a good specification, not the final goal. Embedding meaning directly at the point of use and mapping local data to abstract concepts drives operational efficiency. In modern engineering, a specification achieves success only when its primary design constraint is the downstream reader's direct path to action.